مشاهدينا الكرام، السلام عليكم ورحمة الله وبركاته. حياكم الله إلى هذه الحلقة الجديدة من لقاء خاص. لا زالت طبعا حلقات التواصل أو حلقات اللقاء مع ضيوف إمارة الشارقة المتخصصين في مجال الفيزياء، وطبعا فيزياء الجسيمات وفيزياء الفلكية وفيزياء الكونيات. لا زلنا طبعا مستمرين في تغطية واستثمار وجودهم معنا في إمارة الشارقة حتى نستفيد من علمهم ومن آخر تطوراتهم العلمية في مجال الفيزياء. ضيفنا اليوم متخصص تحديدا في مجال الفيزياء التجريبية أو في التجارب المتعلقة بعالم الفيزياء الكبير. حقيقة هو دكتور أو البروفيسور كارل جاكوبس، متخصص في الفيزياء الأولية، الجسمات الأولية التجريبية من جامعة فرايبورغ من ألمانيا. سوف أحاوره باللغة الإنجليزية. السلام عليكم. Hello, Doctor. How are you?
Thank you.
Well, can we give the audience an idea about the particle physics?
Yes. So I'm working at in Germany at a university, but the research, I'm an experimental physicist, and the experiment itself is built in Geneva, Switzerland, at the European Laboratory for Particle Physics. So this laboratory is called CERN, and this is a big European laboratory where we have now 22 countries from Europe working together to use the same infrastructure and to share the resources to build these big facilities.
That's great. If we talk about the experiments that we have reached yet, what are the latest experiments you came out with?
So the mission of particle physics is to look for the smallest constituents of matter. So what is matter made of? If you take, everybody knows molecules, and then you go to atoms, and then you look, is the atom, does it have a substructure? And then we see that there's electrons and the nucleus. The nucleus, as you know, plays an important role, for example, in energy production. And then we know the nucleus itself is composed of protons and neutrons, and the particle physicists have found out over the past 50, 60 years that these protons and neutrons who are in the nucleus are not fundamental. They have constituents which are called quarks. So we are looking at these quarks today. And just to give you some impression on the scale, on the length scale. So we are looking at very small structures and look what is the structure of the matter. And everybody knows a meter. And now you take a meter and then you divide it in 1 billion parts. Okay?
Oh my God.
That's
too tiny.
If you divide 1 meter in 1 billion parts, then you are roughly at the size of an atom. And then you take this 1 billion piece of 1 meter and you divide it again in 1 billion pieces, and this is roughly the structure which we can explore today in our experiments at CERN.
That's great. Well, if we relate your latest experiments with the achievements that it may occur depending on those experiments, so what kind of achievements we can expect soon?
So, I mean, the biggest discovery which was made in these experiments is 5 years ago. We announced the discovery of the Higgs particle. So particle physicists had one big problem. They explored the constituents of matter. They found these quarks and particles which look like the electron, which have no substructure at the scale of 10 to the, as I explained before. But we could not explain how mass comes into the world and why these particles have mass itself. And for this, there were theoretical physicists in the 1960s. Mr. Higgs was one of them, and they formulated a mechanism how particles could become massive. And the experiment proved that this Higgs field, which is penetrating all space, all vacuum, is responsible for creating this mass. Now you ask for applications. And I must say that today we do not know what is an application of the Higgs field or the Higgs particle.
But we may know it later on.
This is what we are doing is fundamental research in order to explore how is nature built. Yeah, but the applications will come many years later, and there were many examples in history where such cases happened. So, for example, take the 19th century. So there were physicists like Heinrich Hertz in Germany, or Faraday in England, Maxwell. They were all trying to explore phenomena of magnetism and electricity. Yeah, and they did not know what to do with this. It was considered to be useless. Yeah. And you know, today our life would simply not function without this electromagnetic interaction. So, for example, telecommunication and our mobile phones, they all use this electromagnetic force, which was explored in the 19th century, but nobody in the 19th century knew what to do with it. I can give you another example, like Max Planck. He's a famous physicist. He introduced this quantum concept. You may have heard about quantum mechanics and so on. And he introduced a completely new concept that energy is quantized. And this was
moving. Quantity, about quantity.
It's quantized. I mean, it's not continuous. You have small packages of energy.
Okay.
Yeah, and this was breaking with the classical physics in some sense. The physicists around 1900 were a bit puzzled. Nobody knew what to do with this. And then quantum mechanics, a new theory emerged out of this. And also the physicists in the 1920s, when this theory was written down, had no clue what to do with it. And today we can use it. For example, transistors would not function. Or today people are talking about quantum cryptography. To use this to have a very safe way to transmit data. So applications, I'm sure, will come. And I'm deeply convinced that fundamental research, that what we are doing as well in particle physics, is a great foundation for applications which come later. I can give you another example, final one. At CERN, I mentioned in 2012, we discovered the Higgs particle. Now, this Higgs particle is a manifestation of this famous Higgs field, which penetrates vacuum. Now, this Higgs particle does not live for long. It's going to be produced and decays, as we say, into other stable particles. And we have to measure then these decay products of the Higgs particle. And for example, it decays into 2 photons. Photons are particles of light. So light is made of particles, and these are called photons. And these photons, for example, are exactly the same particles which are used as well in medical treatment, in medical investigations. So I'm sure if you go to the medical hospital in Dubai, or in other places in the Emirates, they will have what is called a electron-positron tomography.
Absolutely.
Yeah. And in this electron-positron tomography, you use the same reaction, that electron and the positron annihilate into 2 photons, and these 2 photons are detected with the same devices which physicists like me and others have investigated and explored at CERN for the Higgs discovery.
Great.
So we have applications.
Great. So experiments are always there and waiting for the application, even it will be after a long time.
Well, I would not say we are waiting. We are always trying to do research and development to build new detectors. But these new detectors will then be used in technical realizations and applications. And one nice thing of this research center, CERN, is whatever we explore there, all results are going to be shared, public. So we will publish our results. Also the detector developments will be published. And then also industry companies in the various countries can go and use these applications or these discoveries which we make there. and make applications out of them.
Great. If we will indicate the tools that you are depending on while doing your experiments, certainly your tools should be as developed as technology-wise, between brackets, as the experiment is. So let's have an idea about those tools and the investments that it is based on developed tools.
Yes. So, of course, the tools are big, which we have to use. It turns out that the smaller the structure is you want to explore, the bigger your experimental machine must be, and your detectors must be, your microscope must be. You cannot have a microscope on the table. You must build a big microscope. And so how does the microscope look like? In order to explore these very small structures, we have to build big particle accelerators. Yeah? So at CERN, I was mentioning before, the European countries bundled, so to say, their resources in the 1950s. CERN was born out of the idea that the European countries have to work together. Yeah? Because a single country, it would be too much an investment. And as you know, because of World War II, there was a big brain drain from Europe to the United States. And some physicists and politicians in Europe had the idea to try to build up again science in Europe. So they created this center. And just to give you some impression how large the tools are which we have to use, you have a particle accelerator which has a circumference of 27 kilometers.
Okay.
Yeah? It is in the plain between the Lake of Geneva and the mountains, which are called the Jura Mountains, but it's below ground, 100 meters below ground. Yeah? This is simple because then you do not have to buy the land.
Okay.
Yeah? So you go 100 meters below ground, and then you build very strong magnets because you have to accelerate the particles to very high energy. Yeah? We have protons, which we accelerate on this ring, and they reach 99.999996% of the velocity of light. So they travel with the velocity of light through this ring. They have a huge energy, and then they collide. Yeah? And in this collision, the so-called kinetic energy, the energy of the momentum of the movement, is transferred into energy, out of which, according to Einstein's relativity equation, energy is a form of matter, so we can produce new matter. And the more energy you have, the more massive energy states you can produce. And the produced particle 6 years ago was the Higgs boson, which was not seen there before. So these are roughly our tools. A big accelerator, but then at the same time you also have to build a big experiment to detect these collisions and to analyze them.
While doing some experiments, certainly you scientists, you came up with a a lot of surprises, which leads you to another experiment, which it has nothing to do with the first one.
Yes.
Can you give us a little idea about such events that it happens, of course?
So, in some sense, physics is a field which has an experimental branch. So we are doing experiments and a theoretical branch. So when the two things, they complement each other. Sometimes you have a theoretical prediction of a new particle or a new effect, and then you build the experiment to see if this is really true. Yeah? So for example, this famous Higgs particle I was talking about was predicted in 1964 by a few theorists. And it took 50 years nearly to discover it, because it is not easy to discover. You need the right experiments, the right energy, and so on. But sometimes as well, in the past, it was such that the experiments were made and you found a completely new particle, which was not expected. And this, I think, is the greatest fun, when you discover something which our theory colleagues cannot explain. Because this is also giving guidance then to theoretical physics in what direction to go.
Okay.
Yeah? Finally, the experiment has to decide what is realized in reality. Our theory friends has many ideas. They produce many publications, yeah, because the mathematical formula allow this. But then experiment must decide, no, this is the way experiment has to go. And right now we are in such a situation that we don't have good theoretical guidance anymore. Yeah? So theorists have told us about the Higgs particle, but then from there on, they cannot have a very strong prediction. They were favoring one model, but it seems to be not realized. So the experiment now, our mission is we have to explore the full range of energy and look what is there in order to give guidance again to theory. Okay. So we are waiting for some unexpected discoveries, but I cannot promise that they will come.
The prediction, usually it's related to the theories, to the just theories. Okay, you as through your association, you are experimental more than theoretic. So when can we say that the prediction, it can be as logic as the experiment result?
I think what I maybe did not stress so far is that we have a fantastic theory today, yeah, which is based on the two big pillars of the 20th century. So this is quantum mechanics. I was already mentioning this.
Yeah.
And then we have the relativity, theory of relativity of Einstein. And these two are merged together. And this is what we call quantum field theory. And this quantum field theory was developed in the 1940s, 50s, 60s. Yeah? This quantum field theory makes up what we call the standard model of particle physics. So it describes, we believe today there are four fundamental forces, yeah, which is gravity, electromagnetism, and then a weak and a strong force, which only appear in the microscopic world, the latter two. Yeah, the other two, everybody knows. The gravity is what makes the apple fall off the tree and so on. Electromagnetism I have already discussed. So this standard model describes extremely well all phenomena which have been measured over the past 60 years in all experiments worldwide. Yeah?
That's great.
So we have a precise prediction. Our theory colleagues can predict, for example, they were able to predict the rate with which this Higgs boson would be produced, how it decays. And in the experiment, we measure the decays, and we must say, you are right. Everything turns out as you predicted, which is sometimes a bit frustrating and nice at the same time, because you have the feeling the theory understands what they do, and then the experiment just confirms the theory. So, but with any measurement in physics, like with any measurement in science, you have measurement uncertainties. And our job is to reduce this measurement uncertainty and see if these predictions are still valid with a better precision. But we know, unfortunately, despite the fact that this theory explains all the measurements over the past 50, 60 years, we know that it cannot be the final answer. Because we have some effects in nature which we cannot explain.
Absolutely.
For example, this famous dark matter. We cannot explain today.
If I'll ask you what is the latest about the experimental physics about the dark matter, what you can give us as new?
Yeah, unfortunately, we have not found any explanation for the dark matter.
Yet.
Not yet, no. So, but we have to continue.
No.
So we are convinced that there is dark matter in the universe. It's absolutely very shocking for a scientist. Yeah, I told you about the standard model, and it describes everything well, what we see under controlled conditions in accelerators, in laboratories like CERN. But then you have to realize as a scientist that you can, with this standard model today, only explain something like 5% of the energy density in the universe. And this is quite shocking for a fundamental scientist. So this problem of the dark matter has to be solved, and it has to be attacked from several fronts. And one front is to attack it in the accelerator physics in Geneva, where we have controlled conditions. And I was telling you, if we have enough energy, we can produce new states of matter. And the hope is that we would produce this dark matter particle at CERN in our experiment. Okay? We are looking for this.
But the dark matter itself, it has energy.
The dark matter itself, it has mass.
It has mass.
Yeah?
No energy?
If it has mass,
If
it also has
energy,
at the same time energy, because mass is a form of energy. So it can be quite massive. And so that's why we have to look in Geneva in these experiments whether we have indications that dark matter has been produced. So the Higgs has been produced, but dark matter so far has not been produced. Yeah?
Is the dark matter related to the expand of the universe?
This is more dark energy, yeah, which was discovered about 20 years ago. Yeah, also a big surprise. So the dark, I was telling you, 5% of the energy density is explained by the standard model. Then we have an additional 22%, which is dark matter, and which we see in galaxies, that it must be there. And then we have another 70% or whatever. Yeah, the rest is dark energy.
Let's go back to the particles, Professor. Why particle physics? It has been always called as a power, high power particles. So, can you explain to us what is the relation between the particle physics and the energy or power?
Yeah, it's two reasons why it's called particle physics. It's also called at the same time as you say high energy physics. Yeah, because you need the high energies for two reasons. One reason is, according to Einstein's equation, energy is proportional to mass, E equal mc square. C is a constant, the velocity of light. But energy and mass are proportional. So mass is a form of energy and vice versa. Now, the more energy you have, the higher energy, the bigger, the larger masses you can produce.
That's true.
Yeah. So if you want to make progress and detect, for example, dark matter particles which may have a high mass, you need high energy. So there you need bigger and bigger accelerators. Yeah. And the second reason is, if you want to explore small structures, you also need, again, high energy. Yeah? Because it's related to quantum physics. To every particle, you have a wave character which is associated to this particle. Yeah? Now I give you a nice example. The wavelength of a particle is proportional to the size of a particle. Yeah?
Okay.
Yeah? Now if you have a bag, and in this bag you have 3 iron balls.
Okay.
Yeah? But you cannot look into this ball, into this bag. And you want to find out the substructure or this internal structure of this bag. What would you do?
I have to open the bag.
No. Yeah. But the bag is so small that you cannot open it. I told you the scale. Okay. So what we particle physicists do now is we take a ball.
Okay.
And now if you take a football, yeah, a big football, you would not learn anything about the internal structure of this bag because the ball is too big. It cannot go into this bag.
That's true.
Now, what you do is you have to increase the energy, and then the wavelengths of your projectile get smaller and smaller and smaller, like if you take very small projectiles, like a small a bullet of a small gun, and then you shoot on this, and if this metal bullet now hits one of these balls inside, it will be reflected. It will not go through. So most of your shots will go through, and then you know that there's a lot of empty space in this bag, but some of them will be reflected back. And then you know, aha, there must be hard centers where these bullets may scatter on.
Okay.
This is exactly the way how Rutherford, in the beginning of the 20th century, has discovered that there is an atomic nucleus. Yeah? And the rest of the atom is largely empty, and the electrons are something like a cloud around this nucleus. And we repeat these experiments again. And for this, you need high energy. Great. So this means we kill, so to say, 2 birds with the same trick, same stone. Yeah, you need high energy for the masses. The higher the masses, the higher the energy, and for the structures as well. The smaller the structures, the higher the energy.
If we will talk about the nuclear physics. Let us have a quick idea about it, especially the characteristics of the nuclear physics exactly.
So I would say the nuclear physics is somehow the precursor of particle physics. Yeah, as I was telling you already, physicists always look for what are the smallest structures which we have in matter. And if you would have interviewed a physicist here in 1930, he would have told you the elementary particles are the electron, the proton, and the light particle, the photon.
Yeah.
Yeah? There were no quarks, there were no other fundamental particles. So with time, we learned that there is the neutron and that there is an atomic nucleus and that we have a substructure. Yeah? So in some sense, nuclear physics was the physics of the 20th century, of the first half of the 20th century, yeah, until maybe 1960. And then particle physics took over because the quarks were discovered. And we learned that the quarks are much more fundamental than the proton or the neutron or the nucleus of an atom. So the nucleus is not, the nuclear physics is not dealing with the fundamental forces. If you want to deal with the fundamental forces, then you have to go to particle physics.
That's great.
And to higher energies.
Okay, my final question, actually, Professor Karl, it's about your ambition for the future. What are your vision that you want to reach through your center, precisely or personally as scientist?
So personally, I was quite pleased that this Higgs particle was discovered, because I'm working on this Atlas experiment since 1992. So until 22, it was 20 years of my career. I was spending to design the experiment, to build it up, to take it into operation, and finally we got the data to see that the Higgs particle, this is quite rewarding. Yeah? And I hope that over the next maybe 5 to 10 years, we will have a good chance to discover the nature of the dark matter particle. This would be my dream.
The dark matter, yeah, it's the dream of everybody, actually. Thank you very much, Professor Karl Jacobs, for being with us today. كان معنا دكتور كارل جاكوبس، متخصص في فيزياء الجسيمات الأولية، مشاهدينا الكرام، من جامعة فرايبورغ من ألمانيا. إذا مشاهدينا الكرام، وصلنا للختام، وفي الختام دائما أتمنى لحضراتكم إن شاء الله أنكم استفدتم من هذا اللقاء مع علماء الفيزياء. أتمنى لكم يوم سعيد وليلة سعيدة، وإلى اللقاء.